Just started?
Yeah.
Okay, so we just started. I'm not going to take too much of your time here. It's a Friday afternoon. We have a party to go to at NCAR, and so I just thought that we've had quite a lot of attention given to things called inversions, and I thought what I'd do is I worked on some of these things about 30 years ago and basically gave up for reasons which I'll explain during this brief discussion. Please interrupt. And so what I'm going to do is just give you some step through some of the simplest examples, and then go into at the end hopefully something that I find quite profound. But then I'm the only author, I think, that's ever written a paper on methodologies in solar physics. So maybe you'll find it useful, maybe you won't. I expect it to have absolutely no impact whatsoever on the field, but I think it should. And so that we'll begin with that. So we'll start with something that is, I think, kind of interesting. That is an X-ray image passed through a substance with a detector on the backside, and it's the image of something. And your task, it's not your task, and it's not fair to ask, but is there was something placed in the beam of an X-ray, and it went through and it made this diffraction pattern at the end. And you can see that there's almost no structure in it. It just could almost be a Gaussian. The color tables don't reflect the shapes and anything like that. So all it is you would have to try and sort of guess. This is the essence of an inverse problem. The extra knowledge I'm going to give you is that there is a substance in a solid state in between you and the X-ray detector. And the question is, what kind of substance could that be? Could it be a crystal? Could it be something else? It turns out that it's not fair to ask you. It turns out to be like glass, like something that has no order. It's a randomly distributed set of scatterers in X-rays, okay? So that's the additional information. The point is here, I'm giving you some information, right? Now we go to something a bit more interesting. And this is, you replace that thing with another substance and you put it through and you find something like this. And I ask you again, what is that? Now, if you're a historian of science, and in particular of Nobel Prizes, you might figure out what this is. X-ray crystallography applied to biology. Again, I'm giving you more information here. You know it's X-ray crystallography. You didn't know it's a biological thing. Does anybody want to guess what that is?
DNA.
Huh?
DNA.
DNA. And that is one of the plates taken by Rosalind Franklin, who was then not associated hardly at all, and in fact was given very little credit. Historically speaking, this is my research just tells me that she should have got the prize for producing such high quality plates. Now that thing has a lot of different structures and symmetries in it, which presumably that image alone, I always switch that one off. There we go. That image alone contains a lot of puzzling information. And it took two people with PhDs and a lot of information. They knew it was DNA, they knew it was biological material. They knew the scales on which the scattering was going on, so they knew the geometry of the scattering. Therefore, from the diffraction pattern, there was some information. If it were more than just this, a random distribution of particles, scatterers, the information they had was, they learned from Rosalind Franklin that this was biological material. They knew the scales on which the atomic bonds and what have you and that thing. And so they were able to put all this together with all the other pieces and clues to build this physical model. So what we're going from is we're going from there to there. Sorry, to there. So we've gone from the left picture, and yet the task of an inversion is to get a model out of it that represents what this thing went through, just from the light when measured remotely, okay? The whole point of me stressing this is you've got to have one hell of a lot more information available to you in order to begin to construct something sensible from just an image, okay? Here's another kind of inversion, and this is familiar to undergraduate physicists, at least it was to me. Namely, this is a deconvolution. So on the top, we have three, this is from the paper by Broughton White, 1971. So this is already very well established physics. They were just dealing, or mathematics, they were just dealing with the fact that sometimes we have applications to different telescopes with different point spread functions. So what we have there, we have a fake true profile on top left. We have the instrument point spread function, which is not a Gaussian, as you can see. And then we have the final profile there. And what we're looking at is taking that final profile and finding out what the original profile was. And what you do is you use the convolution theorem. You take the Fourier transform of the top one. That's just a Gaussian. See that? That's a log against frequency there. So that's a Gaussian. It should be a Gaussian function. It's not flat at the top. It's not differential at the top. The other one has a large wing on it. So the profile function. And so what you've got to do is divide that middle left one by the middle right one to do the deconvolution. Now the middle right one has a very small value on the right hand side. So you're going to really amplify any data that you get with noise or with whatever by dividing by something very small on the right hand side. And then what you get is you get the observed profile. And so if I multiply those two things together to the left, I get the observed profile, or if I convolve those two profiles at the top into the third at the top, and then I look at the Fourier transform of that thing, you can see it's a sort of mixture. Now, what I have to do is then divide that thing, the right one, by the one in the middle, the very middle one, the one on the middle right, by the way. And so you end up reconstructing the profile at the end. This is all very well known. I'm not telling you anything you don't know. And so, but it does show you something interesting here, namely that you have to divide by something very small, and in the presence of noise, that's not a very nice thing to have to do. Here's an example of that, we know nowadays we have HAO. We did not have that at the age when Broughton White were writing, and now we have something called different algorithms called speckle, and that's a technique that I don't know the mathematics of, but it does involve an average and trying to divide out an instrument or affected time average profile by the actual data itself. So the data themselves are in the middle. That's the best you can do with HAO, and of course, by applying a reconstruction algorithm, by taking multiple bursts of these images, there's a technique called speckle, which you use based upon similar kind of mathematics to get yourself into a really good shape. So we're familiar with that. So inversions in astronomy, these things are everywhere in solar physics. If you're really lucky, you're going to do an inversion on seismology, and I'll explain why that is different later. Flares, emission measure distributions, what is the photospheric and chromospheric structure? There's a lot of work going on now. What is the photospheric, chromospheric magnetic structure? An even more amount of work. Radio to gamma ray energies, inversions of things like, the formation mechanisms. And then you have Paulman's inversions, which some of you will recognize there as being just essentially extracting one parameter out of a given set of observations. But it's based in inversion theory, all those things there, okay? So what is it that we already know? Well, us in solar physics, we have to deal with things like distributions of material in planets, in atmospheres, in stellar medium. I mean, we never observe a single point, a single atom. If we did, we'd be doing laboratory spectroscopy of like hydrogen atoms, and that's pretty well known already. So we have distributions of things, and we measure, the most we can ever measure remotely from the electromagnetic radiation is the IQ, U, and V. These are measurements of time averages of ensembles of photons. We're not doing real coherent spectroscopy here like in the lab, where you can take individual photons and track these things. We've got ensembles of these things. They're randomly phased in natural objects. They're not all in phase, except in one case, which is maybe a maser or a laser. And so we've got an ensemble of things that lead to some mix of things called linear and circular polarization and just intensity. And we know that the photons carry information about our sources. I mean, we look up and we can see the stars, right? I mean, this is a stupid thing to say, but how do we know there's stars there? Well, there are things coming towards us, and we can split the light up in this different ways. So, but we know that even under ideal conditions, say we measured perfectly everything in the universe with 0 errors for I, Q, U, and V, every object, every pixel in the sky, and on the sun as a function of time. We know that this information is incomplete. We've got 4 n observables, where n is the number of wavelengths. But in principle, we know the physics of these things now after 100 years of quantum mechanics and stellar atmosphere theory and nuclear physics. You know, we've got to have the condition where m is less than 4n. That's just information. We've got 4n measurements, therefore we can't derive more than m things. And that's where the picture of the DNA comes in, the picture of the amorphous source comes in, is you've got to add the information into that thing to really interpret this thing. So I've gone back to real basics here, okay? And in mathematically speaking, we have an equation like that. We have something, the dot, 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 that influences a source S. That could be e to the minus tau, right, for a source function S. S could be an emission measure distribution, and then that dot, dot, dot would be a g of t function, so you want to measure the brightness of the radiation. It could be a contribution to Q, U, and V, similarly, in the same ways. They're not the same as I. And if we look at the numerical implementation of that, the obvious thing to do is to just make a matrix multiplication of the source. And since m has got to be less than 4n, we don't have a square matrix. We don't have the same number of source terms that we're trying to solve for as we do measurements. So we just multiply by a transform of k, make it into a square matrix kt of k. And then that's the expression for the relationship of the above equation with the integral signs. Kt of k can have many dimensions, will have many dimensions, kt, but you can always build this matrix. It could be very much block diagonal, it could be anything. And then you just invert k, multiply that red equation by kt k all to the minus 1, and you end up with s, okay? Now, ktk is very ill-conditioned in the sense that the largest over the smallest eigenvalue. Remember, the eigenvalues you can use the eigenvalues to build the inverse matrix by looking at them on the diagonal. And if you have a very small one, that's like blowing up, dividing by something very small. And so you end up in the same way with the deconvolution theorem. And so what you do is, typically, this is what typically people do. And if you look in Craig and Brown and various other 86 book, and you look at other things, you find out that what they do is they don't actually ever invert that ktk, but what they do is they penalize values of small eigenvalues of that matrix by adding in another operator. And if we were to make that, say, a second derivative, a magnitude, that should be a magnitude there of the second derivative. And that again is a linear system. The second derivative is just minus 1, 2, minus 1 running down the diagonal. Then what we've done is we've actually changed the operator, the inverse operator, to get rid of the small eigenvalues. Another option is perhaps the entropy, the information entropy there that you could use. And you would come up with some kind of, that's non-linear in S, so you'd have to come up with a linearization or something. Linearization works really well. It's rather straightforward to implement a maximum entropy kind of solution. And again, you're looking at finding out something which is the smoothest thing compared with the smoothest solution compatible with the data. So you said to yourself, okay, I've got a really interesting set of measurements here. I don't want to do this. I want to do the least damage to a potential solution that I could possibly do. So I'm going to ask for the structure that has the minimum amount of information needed to constrain the system. This is like an application of the old Occam's razor. I'm just looking for the simplest answer compatible with the data. That's all I'm ever going to do. And I'll recognize that we can't get beneath that. And this is an example of that. There's a picture of a source function from the classic Gene Averett work showing the source functions. On the right is the deep in the solar photosphere. On the left is the above the atmosphere. And this has a chromosphere on it. So the temperature's gone up, but it can't. the source function can't keep up because of the escape of photons. Now, if I have any function f of x that I can add into S to make it such that II is always the same as that plus or minus sigma I. So in other words, if I can add in any old function I want, and I get the same answer for I within the noise, that defines a null space. And that's a really good place to start if you're going to ever try and understand. And this is a sort of linear picture of what's going on with these integrals. Okay, basically inverting integral equations. That's always going to be the name of the game in astrophysics. You never get away without doing an integral of some kind. Okay, so from our work, some of you will recognize this very clearly. I just picked this out as an example. What are we showing here? We're showing contribution functions in the image as a function of height in the sun's atmosphere and wavelength. And you can see the two strong lines of magnesium over here are formed way the hell up here. The wings are formed deeper down. So now what this is showing is if I were to take one column, I would plot a line, and there'd be a small amount of emission, a large amount of emission as I'm going up along one column in the continuum, and then it would fall away completely. So say at 267 nanometers, nothing above that height. But now if I go into one of the weaker ion lines, I can see like those two lines near 268, then I would have a certain amount of emission in the neighboring continuum, and then it would become bright for a period around 1,000 kilometers. That means the function, that K is got a value near 1,000 kilometers. Now we can go to any one of those lines, and one of the beautiful things we can see here is that, and what I've done here is now added a few of those lines in schematically into a plot like this, which was from the CMEX proposal. And you can see all these lines sampling different heights in the atmosphere. And I'm not showing anything nobody doesn't know here. This is all normal kind of stuff. And that's deliberate because this is still an issue. Because look how much those lines overlap. That means the Ks have very, very similar rows. Okay? If those lines overlap, then if two lines are sitting on top of each other, that means two rows of the matrix are the same. That means the matrix is singular. So you can't invert it. That's a trivial example because what it means is that you'd never want to do that. Instead, what you do is maybe you combine those in some way, like add them together, subtract them, put them in a linear combination, and solve on a different basis. Instead of solving for a basis based on the Ks, you solve for a basis based upon a linear combination of the Ks, which are as near as you can make it orthogonal. And that's exactly what they do in helioseismology. Okay. But in solar physics, it's not quite so straightforward. In helioseismology, we know exactly what the Ks are. Not exactly because we've got turbulence in the interior, but on the scales of the sun, they're spherical harmonics. You know the answer before you even started of what these Ks are. Here, we have to compute those Ks, and those Ks change depending on the atmospheric structure itself, which is good, but it's also bad because there's a nonlinearity involved with that. In the helioseismic picture, we're trying to find the internal rotation profile vector of the sun at all vector positions in the sun. And yet the oscillation modes that we can measure are totally independent of that structure. It's a linear problem. Okay? This one is not. Here's an example of one for the differential emission measure. So instead of the rate of transfer problem we just looked at, this is now recognizing that the sun is black at UV wavelengths, and we just have emission lines, and those emission lines are contributions from this is just a relative level population, but it shows you that we've got and these are all with the same principal quantum number as the ground state in each ion. The details of that aren't really important here. But what I draw your attention to is as a function of temperature, these are the same kernels. So we've got kernels that pick out carbon-4 at 10⁵ Kelvin, C3+, carbon-3 centered near 4.8 Kelvin, and carbon 2 beneath. I didn't include carbon 0, so it doesn't drop off. And then carbon 4 plus, carbon 5 plus. That's carbon 5 and carbon 6. What I'm trying to show you here, that again, we have duplication of the shapes of these lines. So this is an infrared line. This would correspond to an infrared line of carbon 2. This would be a resonance. One of these would be a resonance line, another one would be an intersystem line, but they all have more or less the same shape. Again, that's telling you that the matrices have a lot of replication in their rows. So you don't really have, and so you need to be clever about the way you do that. Again, not a fundamental issue, but something that's interesting. So what I've done here, what does this mean? The need to invert, I've inverted it too, apparently, as well, KTK. There is such a thing as a condition number, and such that the determinant, if it goes to 0, we have duplicate rows, then we end up with an enormous condition number, which is really bad, the maximum eigenvalue of the smallest eigenvalue of the matrix. And I just want you to consider 2 rows identical, except for noise, say, some different parameter. So this could represent, the top row could be carbon 3 resonance line, the second row could be carbon 3 intersystem line, or something like this. I mean, it's just epsilon. Let's assume it's a small parameter compared to everything else, and then a completely different line here, which is formed at higher temperatures, say. So what's going on here is that we imagine if we make epsilons all small, then we're getting closer and closer to redundancy in that matrix, and we're getting worse and worse and worse eigenvalues, spectrum C. And remember, the smaller the eigenvalue, the more we amplify garbage in our inversions. So what do? We change the matrix. We change the matrix. We've changed the physics. We're asking Occam to come and save our asses, John of Occam from the 11th or 13th century or something. And so we're going to replace M with this lambda of S, and that's a functional, or it could be just a simple linear function, like I said, second derivative, and we invert that one instead. So here's an example of such an inversion. Right now, this is not what they did. They did something that's you can show is more or less equivalent. And what they did was they took all those observations of from Venus regions of the quiet sun. This is between 300 and 1350 angstrom, and they said each line is formed at a certain temperature. So this, for instance, could be carbon 3, carbon 2, carbon 3, carbon 4, silicon 3, whatever the hell it is. I don't care what it is, but this is what they found from those spectra. And it's a lovely part of the spectrum to do this kind of work. And so then you invert this to get psi of t, but you do it in a way which allows it only to be smooth. Notice here, there's no high frequencies in this dash, in this line here. And that's because you could add any high frequency noise to that and get exactly the same answer. So this is the simplest answer they could find that they thought was compatible with the data, and you would get something similar if you did formal inversion. What is this thing, psi of t? Well, it's nothing but this. So if I look through a plasma, through a line of sight, and I'm intersecting various kinds of things, I find, and I plot just the distribution of densities along the line of sight from S to the I, and I do the same thing here for temperature. I basically take everything between t plus dt, and then I find the value of n, and then I add them up and make it that. That's what it is. So you can see that, this can have a contribution from here, from here, from here and here, and from all intermediate points. And there's only with a radical assumption would I assume that this thing represents one structure along the line of sight. That's a radical assumption. You've told it that it can only ever have one contiguous function along the line of sight. And what people typically do then is they do the regularization. So how come this is so-called respectable? Well, I put it in quotes here because there are books written about this. There are papers published with Tikhonov regularization, which is second order or first, or even zeroth order regularization by changing the damn matrix. And you get answers out of it, and you accept that you can't learn things below a certain size, and you get the smoothest answer. The other way of doing this might be to say, well, in an actual fact, we've got an atmosphere that's a chromosphere covering 9 pressure scale heights. And I could use 1,000 lines to move along this thing. If I carefully trained it, I would get individual pieces of information through the chromosphere. Each of potentially, 1,000 different points in principle, maybe, if you had sufficient signal to noise. But that's not what people do at all. They measure from the ground certain lines, and then they say, well, I'll measure iron, I'll measure calcium infrared, I'll measure the wings of calcium infrared, I'll measure sodium 1, and I'll add in calcium K, and I'll measure IQ, U, and V. That hasn't been done, but it's been close to being done. Okay, but you only do it at 4 depths, because you recognize that getting all this information for all the lines is just it's not going to be tractable. And then you say, well, I'm only going to allow smooth solutions between these things. Sometimes people get clever and they allow for one discontinuity in it, or something like this. This has recently been done in Sweden, for instance. But any solutions to the source function you're going to get out of this thing, and the contribution functions, is always going to be smooth unless you make it explicitly otherwise by doing such a thing like a shock. Another way to do it is to take your kernels and try to get an orthogonal set of kernels out of that. So you would take your things in helioseismology, for instance, and get this beautiful kind of set of things which are locally sensitive. So I would measure a set of 7 nodes, specifically chosen because when I add those nodes in a certain linear fashion, node 1 minus a half of node 2 plus a third of node 3, whatever it is, I end up with a quasi node that looks like it's got a peak right at the bottom of the convection zone, as narrow as I can make it, so I can get the differential rotation right there. That is an optical localized kernels, and it works for linear problems like seismology. The other, I think, more respectable strategy is to don't attempt inversions at all. I would say that the seismologists, that's the last biggest breakthrough in solar physics, was 1989, when they started to be able to see that the sun's rotation was not at all in the fashion that some people expected. And Matthias can explain why on the basis of things like Reynolds stresses and effective viscosities and God knows what else. So what else can we do is something I was told last year with a HAO awardee. Well, I think you need to think harder about the problem. This was not in this particular problem, but it reminded me of this inversion problem. And so, for instance, if you're observing the corona or various things, what else can you do to compare models with data? Well, there's actually a hell of a lot you can do. You can actually try to define what the basic properties of things like microturbulence in homogeneities are across the Doppler disk or within a coronal or across a coronal loop. That's not been done still. I still don't understand why that hasn't been done. They don't build spectrometers with sufficient resolution because they integrate over the line profiles and differential emission. Or you can look to better methodologies.
What you said is a very interesting point, that kind of integrate over the whole spectral line, and I'll come back.
Okay. So inversion is a weak methodology. First of all, it mixes theory with data completely. If you can't do the forward problem KS, you can't do the inverse problem. And then you change the K, which you're not allowed to do physically. So there's something really fishy going on here that makes me very uncomfortable. And what it is a mix of theory and data. You find source under integrals. It's an ill-posed problem because I said you can get around that, and this is where we're going. You've got to add information. But the real question is, where are you going to add that information from? And this is where people like Matthias come in. Because you can add a lot of information from the computations. How does one know if one is wrong? How do you know if you're wrong? Can you put an error bar on your differential emission measure that you think is meaningful? I would say no, because you changed the bloody kernels. You can't do that. Non-uniqueness. The reason global seismology is because of those reasons I listed there. So with a mix of theory and data, let's look at what a strong methodology is. Well, you can just look over new horizons. You can set up on Beagle and try and find out some new things. you can observe the sun in different ways, and you just don't need to keep observing EUV lines that are unresolved forever. That doesn't make any sense to me. You can seek to reject models and assumptions. In other words, hypothesis testing. Now, this is not easy, and it's partly why I'm retiring, because I can't find problems that I can do that would really do that. I've published some in the last couple of years about the corona, and I'll show you one. What you've really got to do is to confront theory and predictions with data. And so that's going to take some very obvious things. First of all, you've got to make your assumptions absolutely explicit. You've got to cleanly separate theory and data. Don't mix them up. Don't assimilate data and expect to find something that's going to give you an advancement in time that you can then test against something. All you're going to do is, when you find it doesn't agree with your data, then you update your initial condition and start again. That's not science. It's not natural science. You can do numerical experiments. That's a wonderful thing. Mark Misch has been talking about this. Matthias represents some of the best people at this kind of things. The other thing you can do is pose every problem as a Bayesian prior and try to test that prior. And you can use multiple priors and find out what the probability of each data set is given with that. In thinking like that, you don't end up just observing the sun and saying, oh, well, I found this thing and it looks like a shock wave propagating up. Therefore, if we assume it's a shock wave and it's propagating up, then what are the consequences? Oh, and we find it doesn't fit the corona above. I'm sorry, that's not useful. This is why a lot of papers in solar physics aren't of any interest. They're not even wrong. How to define the problem? This is the tricky bit. This is the bit I don't know how to do. You've got to think about what you really wanting to get out of your work, and is the information ever really going to be added through the physics? You can do it with the computation-informed methodologies. There are various points I want to make here that you can look at, maybe look at afterwards. But this basically is the question. Say you get a magnetoconvection simulation, this quote simulation, it's absolutely beautiful. And you end up with an outcome. You find some kind of statistical disagreement with the sun. That's usually what you're going to do. Meaning that, I mean, you're going to get a bit agrees with it, something that's not going to agree with it. Or you can end up with a complete disagreement. In other words, there's some aspect of the calculation that never does anything, and yet the sun does, right? So you think to yourself, well, this is where the bulk of the studies are published. And you end up with going, it's not even wrong. I mean, what am I going to make of this? You've got some disagreement, some agreement. I don't think this is advancement. Complete disagreement. This is the absolute best outcome you can ever get from a numerical experiment, I think. Because then you've really learned something. Something the sun is doing is definitely not in your calculation, for whatever reason. That is the moment of creation, and that's what we should do. The problem is that when you get most results in some disagreement, you have to ask yourself, then what? And then you go back and you say, well, what was the goal of this work in the first place? I don't know. I really don't know. Let's just point out that I think the word simulation is not a very helpful one. I would much rather use numerical experiments. The difference being that I think simulations are intended to be compared with observations. And I'm not sure, unless you get a complete disagreement, that that's useful. Numerical experiment is a much nicer thing. You've actually got a system with well-defined boundary and initial conditions and what have you. You've got your physics in there and you're calculating, and then you can synthesize an image and you can say, oh, look at that image. I've got a 2D version of this. I wonder what's going on in the other directions. That's the kind of thing you're learning from, right? And there are just a couple of sayings that make this interesting to note. You pays your money and it takes your choice. I mean, you know, there's a choice being made here. I'm not going to say that people are wasting their time and just doing things. It's just that I think we're spinning wheels a bit. Is all this semantic? Wherever we observe the sun, we never get down to the result scales. There's something going on underneath the scales we're looking at, which is significant compared with the sound speeds. It's maybe a fraction of the alpine speeds in the corona, but those things never go away, and we better damn well understand what that means somehow. And I don't know how to do that. But I do know that there are discontinuous solutions, even in MHD, let alone plasma physics. Highly inhomogeneous transport, there's turbulence and chaos. So you've got to be careful about how you frame your questions. And certainly inverting data in the presence of all those things there makes me almost feel sick when I look at what we actually know about MHD and inhomogeneous transport and these things. We need to refine the questions. Is the data we're getting sufficient to refute our hypothesis? Why do we care about measuring N and T? It's the end outcome of a whole lot of interesting physics going on, but it's the last thing to change in response to more forces, say in the high magnetic field plasma. The N and the T's are just the end product of something that's happened. The plasma's got heated, it's got a certain density. It doesn't tell you how it got heated. So these things are not very interesting. I think we need to formulate problems. Let me show you an example of where I think one can go wrong. We saw this before. There's a differential emission measure. And we can use that with an equation for heat conduction at a constant pressure to build an atmosphere that looks like this in this shaded region. Everything's hunky-dory. It's all in one place. And the top part of this thing fits. That from 10 to the 5 up, it's no problem. Here, we get a complete disagreement, which means that something's going on down here in this 1D model. And here is the 1D model. This is one made by Gabriela. So here's the 1D picture. This is assuming that there's a continuous transport of energy from the corona down towards the chromosphere, and that's the answer you get. These are data I've taken of published recently. Here's the line of sight magnetic field in the chromosphere. So this is above the height where the magnetic field is filling, and is rather strong. See that 600 Gauss. So this is way down in the chromosphere, a few hundred kilometers. So above that, everything's very, very strong magnetic fields. Here is the chromospheric intensities. You can see these nice fibrillar-like things, but the really strong stuff is centered down here over where the magnetic field is pretty strong. This is iris, and you say, well, look, is this iris data connected to the corona here? You could say that by looking at, let's compare this one with this one. And you go, oh shit, look at this. This is really hot. This is, oh, there's no emission there. You can look at AIA 304 at the same time. This is co-temporal. This is not co-temporal quite. This one is. This is about an hour apart. But these loops don't change much over an hour. What I'm saying is, there's no obvious evidence there's any physical connection between this region here. And that's occurring on scales of a few arc seconds. That's the length scale over which we can best observe these things. And it says that on the smaller scales, like the remaining microturbulence that we haven't explained at all over the atmosphere, there's something going on at smaller scales, which when you blend that in, say I replace that with 1 pixel, and did that all over the sun, I'd end up with a nice 1D correlation between the chromosphere and the corona. And yet here is no sign of that in a typical kind of active region area. Recently, we heard from a very interesting talk by Christoph Keller. Well, we want to invert everything everywhere all the time. Okay, so let's take a quick look at this. In essence, and I read the paper, I didn't get to the details of everything yet, but I intend to, because it's very, very interesting and a really provocative way to do things. But what it is he's basically minimizing a Lagrange undetermined multiplier times each equation of motion, and minimizing that plus the chi-squared from the observations. And he showed some remarkable data where he used continuum observations of the sun, of the visible light, and showed that it could reproduce, he synthesized those with Boulder code, and then he inverted them using this scheme, and he came up with something a little bit similar, quite similar in many ways, but there were significant differences. But let's have a look at what's underlying this. These equations of motion are not there to be approximated. Those are, given the physics you know, those are exact. Did B is not approximately equal to 0, it's 0. Furthermore, curl of B, if you want something interesting, like why is the curl of B interesting? Well, it's the Lorentz force, it's the thing that's dominating the force balance above a certain height, not in a photosphere. But if you want that thing, you've got to differentiate the solution. Well, you've already kind of smoothed things out by putting in, and you've combined theory and data here explicitly to start with, which I think is not a very good idea anyway. And you know that there are weak solutions, discontinuous solutions, posed as an integral equation instead of a differential equation, that the differential equations just smooth over arbitrarily. So you'd have to have enormously dense grids, and yet with his formalism, the grid is set by the observations. The observations grid is set by the telescope and by the seeding. It doesn't make any sense to set a grid of a numerical calculation on the basis of what an observation is. You don't know you've got a telescope and there's an atmosphere and you're looking through it. The sun is going to do things, and it's going to do things in magnetic Reynolds numbers, which are orders of magnitude larger than anything that would state that you need to use those kind of resolutions. The thing I have a real problem with is how can these solutions be meaningfully wrong? Furthermore, how do you extend it above the photosphere? So one of the technical things I don't quite understand yet, but if you've got these are a set of PDEs that require initial conditions, boundary conditions in 3D. And he gets around that somehow by forcing a certain amount of energy through the atmosphere and having a radiative loss energy equation in there. And again, I'm not quite sure what's going on here, but I don't think that can be applied above the photosphere. I think you have to solve so consistently for everything, and it'd be overwhelmingly difficult calculation to do in any meaningful sense. And then if you can't tell if the solutions are actually meaningfully wrong logically, I mean, you don't have a pure observation that you can compare with, because what you've done is you've taken this and you've fixed a model into it, and then you've advanced it in time, and you say, oh, well, we've got some differences. I don't see that that's particularly good science, and I don't think there's a real science question being asked there. If you want to know if a flare is going to go off, fine, you know, enjoy yourself, go for it. So, in conclusion, because we want to get done here, the really important thing I think to me is that in remote sensing, we're always dealing with integral inversions, and that almost never any kind of solution is determined by the data alone. I'm not telling you anything you don't already know. This is manifesting through to everybody the moment they start thinking about astronomy. Even as kids, I think probably, oh, how do they know this is a G-type star? You know, this is so. If it sounds offensive to you, I'm not trying to be offensive. I'm just giving you a step back reminder. What is a weak methodology? Well, if you mix data with a model and then you come up with something, and the easiest way for me to say that is to you know, let's build a sequence of photospheric models and let's compute line strengths and let's find the abundances. You know, that's probably just fine, because when you look at the details of that and you look at the granulation and you've looked at all these other things, you can look backwards now with that knowledge that you have now that you didn't have when people were doing these curve of growth studies in the 30s and 20s and whatever, and you find out that the hydrogen spectrum actually shows you you've got more hydrogen than anything else, you know, in Cecilia Penka-Bosch kind of stuff. But when you do this, how will you know if you're wrong? Well, you know that you're not wrong in the situation I just gave you, because people have done those simulations and got granules, they've got the primary motions in place. There is a bit of microturbulence, but the microturbulence doesn't enter the curve of growth to the extent that it's going to affect the measurements, the question you're really asking, which is what is the abundance of these things. But in a general case, if you have something more complicated than the photosphere and say the chromosphere, how will you ever know if you're wrong by combining inversions with data, numerics with data? I would say that because we're dealing with plasmas above the surface of the sun, in which we have this condition, we have such incredible differences in transport that essentially everybody ignores transport across the fields. But that can't be right. Along a field line, somewhere along each field line in the corona is coming down into a region where there's a lot of neutral plasma. And that neutral ion and ion kind of exchange is quite efficient. There's a thing called charge transfer between protons and hydrogen atoms. So what I'm saying is that the assumption that there's just 1D transport is manifestly not wrong at the top of the not right at the top of the chromosphere, and yet we have never really had a proper calculation to figure out what the magnitude of those effects are. The ratio of ion to the ratio of perpendicular transport to parallel transport goes as t to the power of 10 or something. So what that means is that if you go down to 10 to the 4K, 10, it's some large number like 8 or 10, it's 7 halves squared or something. No, 5 halves squared. So it's 5 halves times 2. So it's t to the 5 at least. And so you end up with 10 to the 10 times more transport across the field for a given gradient than the other. Of course, we don't know what the gradients are. We really don't. But we do know, people publish a lot of stuff saying, oh, a lot of chromospheric material ends up at these heights, and we see prominence. So there are things in here that are very interesting to me. And I would say that a strong methodology requires us to think more about formulating problems. We can do a well-posed inversion, seismology is one example, and then we would need to map out the null space. They know that the high order spherical harmonics, we can never learn about differential rotation below a certain scale because of that factor, aside from the fact that we know we've got convection, and that those things are also a major component of the velocity field that you're kind of averaging over when you take the bigger kernels that you can really use. And I think really, at the end of the day, we should probably think about refuting models and assumptions and hypotheses. And one way to do that might be, one example I would like to study is, let's take a coronal, a nice active region that's not doing very much. That's not a contradiction in terms of these things can last a few weeks. But you might be able to find a loop that's sitting there being heated nicely, which would otherwise cool on a time scale of an hour, and then it lives a lot longer. And then follow it across the solar disk and look at the line profiles at different angles relative to the magnetic field. Then you're starting to look at the anisotropy of the magnetic fluctuations. And I think that is the thing that would give us a nice clue on what's heating the corona. So it's Friday. That's the end of the presentation. And I appreciate people listening in, and I appreciate everybody coming here. And we have a party to go to in 15 minutes, 10 minutes. But if anybody wants to say, Phil, you're full of shit, I would be perfectly happy to accept that.
Or if you have questions.
You can what?
Or if you have questions.
Yes, maybe you have some questions. Thanks, everyone.
Thanks.
I think the hard part is always how, at this point you bring up here, how to avoid mixing data and models since we do remote sensing. And it's very difficult to make sense of remote sensing data without at least already putting some model in there, right?
Yeah.
But it's a kind of intrinsic problem to astrophysics. That you actually, in some sense, you can never really cleanly do what you would like to do here, that you really can refute models with a clear measurement. It seems to me more the best you can do is you can see if you arrive at a consistent picture degree.
So I think, let me give you my favorite example of something that seemed totally unreasonable to me when I was a kid and looking at this and learning physics. How in heaven's name do we know what nuclear processes are going on inside stars? And the crucial information was not only the nuclear physics later on, but it was the fact that stars occur in clusters. And so now you could look at how, with a reasonable set of assumptions about this cluster is not much different from that one over there, from this one over here, that one over there, and you can look and make this thing called a brightness color diagram. And they all line up. And that main sequence and the giant branch could not be constructed from field stars alone. You have to use clusters. And so what you've done is you snuck through the back door by taking out the large source of systematic error you could possibly get from it by choosing clusters and making the hypothesis that if it's that big on the sky, it's that distance plus or minus that much away. And we know that all these stars, therefore, if this distance is 100 compared with that, we know that all stars are measured to be 100 plus or minus 1% away. And now we can say this has got to be proportional to luminosity. And then we can use some other physics to say the temperature. There you've thrown away the stuff that's killing you, absolutely killing. And when I was a kid, when I first realized this, I thought, who the hell thought of that? It was someone like Hertzsprung, right? Or Russell. I mean, that's just genius to do that. Now, the number of things we can do in solar physics like that is probably rather small. But we do have Parker, and we can observe sideways on, and we can turn these horrible inverse problems that you get from one position into much more tractable inverse problems when you observe the same thing from different positions in space. And I think that's something I didn't mention here. But do you buy that argument? I mean,
to some degree, yes, but I have the feeling the more we go down into the details in solar physics, more complicated, higher resolution whatsoever, the further we go down this path, the more physics you have to involve at the onset to make sense of the observations we're getting. I think this clearly separation between data and model was easy in the beginning of solar physics. But the questions didn't dig down into the tiniest details, but the further we go down these rabbit holes, the more messy it becomes.
right, but we still don't have answers to some of the most basic questions in solar physics.
In some degree, because unfortunately the most basic questions require some of these rabbit holes, it looks like.
Yeah, well, I think we need more people that are like a horse. For a horse, a rabbit hole is a dangerous thing. It puts its horse in, it breaks its leg. So it needs to be more like horses, where we avoid the rabbit holes and try and get up the hill to the top of the hill anyway. And I'm just encouraging, when I talk to young people, I try to encourage them to think like that. It may not be possible, but damn it, we have people like Feynman coming along and changing the whole of physics in one occasion. And I don't see any reason why we shouldn't challenge ourselves. And at least some of us should be avoiding the rabbit holes to try and find ways around these very, very difficult questions. And I'm not sure we've been doing that because I don't think institutions support that kind of research. I think institutions support incremental research in the rabbit holes. And you end up finding quite a lot of baby rabbits and some rabbit poop and maybe a bit of rabbit food and other things. But you don't find out a way to get around the rabbit hole and up the hill to the top where the answers are. That's how I feel. People know that. I mean, you haven't heard anything new from me today that you don't already probably know about me. But I thought, given the inversion talks that we've had recently, I would like to remind people of some of the things that I think are important to remember, and certainly go down the rabbit holes, because it's Alice had a great time in Wonderland, right? I mean, it was amazing, all these new things she found out. But I think we do need some emphasis on the avoiding that and doing some really basic thinking. I don't think you can think too basically about the sun as an object.
I actually, when you mentioned about inversions, it was very recently that I came across is that how we were inverting lines are done. We were doing the summation of the whole spectral line. But then when I started, I think I emailed you about this. When I started looking into individual line positions, the sunspot became a lot differently, and I couldn't understand which of those individual observations are the true ones, right? So so then I decided, for simplicity, when I have the lobe of the line curve, lobe of the line profile, I just use the center of the line profile and within a certain range where I feel that the physics doesn't change much as my my magnetogram, or assuming that I'm fitting only that part and the inversion codes. Because
I think you've got to use I mean, you're talking specifically about Stokes profiles of
Yeah.
sunspots, right? See, in that case, it's pretty clear you've got to use at least a weak field approximation, which samples the whole profile, if not a full-blown vector inversion, using the forward calculations that people know how to do. And so what they know how to do that forward calculation, if you look at Jeffrey's license to manage, I mean, all the information is in there for the classical approach to Zeeman polarization. It's perfectly fine. So you can do quantum corrections. So you got to use a whole profile, but when people use the whole profiles, it's mostly done in coronal physics these days. You know, it's always amazed me that people build spectrometers with a few hundred resolution, maybe a few thousand. You've really got to do 20,000. I mean, 30,000 resolution is 10 kilometers a second. And a lot of coronal lines are broadened by about 20 kilometers a second, more above and over and above. And so it seems to me as if if you were to sit, for instance, an observation I'd love to see, just looking over the horizon, like I said at the beginning, strong methodology, just look over the new horizon, is to take some spectra during eclipse with 1,000 to 1 signal to noise and a resolution of 100,000, just to see what the hell is lying around at the bottom of the 10.830 and the 10.747 lines. Because if heating is going on by fast particles, right? If a little bit, which is some hypothesis people have made, be it electrons or protons or whatever it is, you've got to see something in these ion wings eventually. And that hasn't been done.
But that's the whole thing, right? Like, so sometimes people just don't use the wings of the lines.
And there are good reasons why you'd never be able to do that from the ground without an eclipse, right? In a corona. But you could do it with EUV lines if you just sacrifice spatial resolution for spectral resolution and did an experiment like that. People are obsessed with what can move on the sun. And what you'll read, what I was astonished a few years ago when Nuruddin Rawafi said, oh, the sun's atmosphere changes everywhere all the time very rapidly. And he proceeded to show me a movie of granulation, which had been speeded up by a factor of thousands, so you could see the stuff coming and going all the time. So then, but then they'd shown me this image from Solar Orbiter of a solar corona doing absolutely nothing for like 3 hours. Absolutely nothing. That's not dynamic. But they will find little bits that are dynamic. Say, oh, look, that's dynamic. That's like going out to a field of grass. You're interested in the grass, but you say, look, there's sheep moving over there. Not the same thing. Party time, guys. I'm actually supposed to be there because I'm an honoree of some kind.